Greetings to all stakeholders in the South African mining industry. My name is Ray Durrheim and I hold a research chair in exploration, earthquake and mining seismology at WITS University. And I'm going to tell you about some really interesting research that I've been doing with a postgraduate student, Nandipa Masondo, looking at the use of thermal spalling as a way to mine. Now, what is the challenge that we really try to look at? Well, I suppose we can look at it as a mine, as a factory, where we are trying to produce a product, which is ore, and we want to do this safely and efficiently. And the way most mining in South African deep gold and platinum mines done currently is by blasting. Now, we're looking at methods that can produce ore 365 days a year, 24 hours a day, 7 days a week, with minimum dust, fumes, and stress change. And the technology that was identified and that we've been looking at here is something called thermal spalling. And I will just briefly go through the work that has been done over the last year or so, where we've done a literature review looking not only at spalling of rock, but other ways in which you can cut the rock. We've done petrographic studies of gold-bearing reef, and also, and this is what I'll be showing you here, are some laboratory studies of the spallability of gold and platinum-bearing rocks. Now, this all really started in terms of one of the other SAMURDI projects or themes called non-explosive rock breaking. And there they had a team of experts looking at the most promising technologies that could be used to maybe replace drill and blast. And here you see two graphs over here where there's a whole list of alternative technologies. Many of these have been tried in different environments and are even used in practice. And you can see that the two most promising technologies, and those are the tall columns on the right-hand graph there, are rock cutting using either diamond wire or diamond saw or thermal spalling. And so my interest has always been here looking at the way in which rock deforms and the rock breaks. Now, rock can break in a nasty way, causing earthquakes or rock bursts, but of course you need rock to break in order to mine it. So here our interest over here is not looking just at blasting or mechanical rock breaking with hammers or drills or picks, or chemical rock breaking where you put in chemicals to perhaps expand and crack the rock, but over here using thermal spalling. Well, what is thermal spalling? Thermal spalling is a technology where you apply a very intense flame to the surface of a rock, and the rock then starts to flake and chip. Now, this technology that has been tried here in South Africa is in fact patented. It's been successfully implemented in Canadian gold mines, and also it has been used here in South Africa, and a company called Maxim with Mark van Schaik as the chief engineer and owner of the company is the local representative. And in fact, successful trials were done in AngloGold Ashanti's mines. And what we really are doing over here is trying to take this a step further. We know that it can work, but we need to make it an efficient technique. And so we need to know how to fine-tune it to different rocks in terms of their grain size and mineralogy. So here the idea is that we have a thermal shock being put to a rock, and over here we find if you only heat a rock very slowly, it warms up, it doesn't crack. If you do it perhaps with too intense a heat, the rock can actually melt. So you need to find that sweet spot over here that will create the flaws and eventually cause it to detach. So here I'm going to just review the research that was done with a group from WITS University with help from the Mandela Mining Precinct, and of course Maxim Engineering played a key role in this. So we're going to look at the rules, we need to understand what governs the breaking of rock so we can work out how to optimize this. So we've been shown that it can work in gold reef, and one of the key questions was, well, what about the platinum bearing reefs? And what we've done over here is to look at the details of the spalling process and the fracture mechanics. On the top right over there you see a flame, and this is just over here for our tests. We used an ordinary oxyacetylene torch, but of course you can change the gas mixture, you can change the temperature of the flame, and in the bottom left you'll see a rig in which you put the rock sample, and you can see the sampling the rock moving from left to right. And this allowed us to do a whole range of tests over here. The samples that we used were, of course, we had various samples of WITS quartzite with different types of quartz pebbles in them, different grain sizes, and we also had some Merensky Reef pyroxenite. And we also had some UG2 chromatite. And so let's look at our first test over here. What we find, of course, is what is critical is what is the composition of the rock. And there are many parameters that affect it. Existing microfractures, the mineralogy, the grain sizes and shapes, the porosity, the strength of the rock. all these are factors that affect the sweet spot where spalling is most efficient. So Nandeepa did a whole lot of petrographic studies where we make thin sections of the rock, basically microscope slides, and in there you can identify the sizes and shapes and quantities of the different minerals. First was for quartzite, and this is the example for chromatite, a very different rock type. And of course the question is, would it spall as efficiently? And here's the pyroxenite, again a different mineral assemblage. So the question is, what is it that really controls the spallability of rock, and what would be the sweet spot in terms of the duration and intensity of the flame in order to get optimum flaking? Here's an example of some tests that were done. That's the quartzite rock being moved in front of the flame. You'll see that spalled very efficiently. Many flakes and chips were thrown off, were ejected. Here you can see the sample afterwards, and you can see the thermal erosion of the sample. Now we look at a different sample over here, and we'll go more slowly and look at the chips that are thrown off. Not nearly as dramatic, and in fact when you look at it more closely, you can see there are little blobs over there, and that is rock that was in fact melted. So over here you can see this was not at the sweet spot. And so what did we find over here? Well, there is an equation that's been developed that in fact predicts the spallability of rock, and there are many different factors that affect it. Perhaps things such as the saturation level. We did things such as putting our specimen and soaking it in water before or after. We also found things such as the angle of the torch, things such as the flame temperature, the type of gas, the gas pressure, and of course other kind of pre-treatment that we might have done to the rock to weaken it in some way, and of course the in situ conditions. So this is where we are right now, and where we plan to go further, of course, is to take this and do microanalysis to really find exactly how this process works, and to find out how we can optimize this technique. And what we're hoping to do, and we're not quite sure when this will take place, are some underground trials, because of course it is one thing to have it working on a small scale on a laboratory bench. It is yet another thing to scale it up into a routine and efficient underground mining method. Thank you.